Hello students, welcome back to CLARI Concepts Unleashing Conceptual Learning. Today in this lecture we will be talking about the numerical examples, mainly looking at the pressure variation in the static fluid, particularly in the vertical direction, right? So let's go back to the numericals. So very first numerical I have is an open tank contains water up to a depth of 2 meter and above it an oil of specific gravity 0.9 for a depth of 1 meter. Now see, here what is given to you? Firstly, an open tank that contains water up to a depth of 2 meters. That means I have a tank and water up to a depth of 2 meters, for example, right? And above it, an oil of specific gravity 0.9 for a depth of 1 meter. So above this water, there is an oil, layer of an oil up to a depth of 1 meter, right? And this oil has specific gravity of 0.9, right? So let me just write down the given data. I have been given specific gravity of oil as 0.9. Okay. Find the pressure intensity, number 1, at the interface of the two liquids. That means somewhere over here. Okay. And at the bottom of the tank, that means somewhere over here, for example. So let me mark 3 points. One is point number 1, 2 and 3. So my target is to find the pressure at point number 2 and pressure at point number 3. Alright. So what I will do? Firstly, I know that if I want to measure a pressure at point number 2, I must have a pressure at just a point above it, right? So if you talk about point number 1, this is open, right? So it is exposed to atmospheric pressure. So I can say P1 is equals to P atmospheric. And if you take the gauge value of this pressure, it is 0 Pascal, right? The atmospheric pressure is 0 Pascal gauge. And if you are unable to understand what is gauge pressure, I request you to go back to one of my lecture where I taught you what is gauge pressure, what is absolute pressure and what is vacuum pressure, right? And also before going to this numerical, I request you to go through the lecture of hydrostatic law. Alright, so if I know pressure at point number 1, I can find pressure at point number 2 using hydrostatic law, whereby, just a minute. Just a minute. Okay. So I'll take the example and I have the water oil, and now I'll put the given data is specific gravity of oil as 0.9 and the pressure, let's say this is point number 1, point number 2, point number 3. Pressure here is atmospheric on this surface, so I can say P1 equals to P atmospheric equals to 0 Pascal gauge. Yes. Alright. Now, using hydrostatic law between point 1 and 2, using hydrostatic law between points 1 and 2. What you can see? Pressure at lower altitude point, that is first. So, which one of this is lower? 2 is lower. So, pressure at lower altitude point equals to pressure at higher altitude point, that is 1 plus rho GH. Now, let us say this is 1 meter is your H1, this 2 meter is your H2 and density of oil is rho, density of water is rho W, right? So, here rho will be what? Fluid between 1 and 2 is oil, so this will be oil and H will be 1 because distance between 1 and 2 is 1, simple. So, I got the answer 0 plus what is density of oil? Specific gravity of oil is given to me as 0.9. So, density of oil will be equals to Sg of oil into density of water, and I hope you are aware with this. If you are not aware about this, you can go back to my lectures of fluid properties. Sorry, this will be 900 kg per meter cube. Okay, so density of oil is 900 into G is 9.81 into H is 1. So simply calculate the value from this 900 into 9.81 into 1, that is 8829 Pascal. Again, this will also be a gauge pressure. Why? Because this was gauge pressure. So in this equation, if you put gauge pressure value of this particular P1, you will get P2 in gauge. If you put absolute value of P1, you will get absolute value of P2, right? This is the answer. So pressure at the interface of two liquids will be 8,000 8,829 Pascal gauge, right? All right, now let us talk about the pressure at point number 3. So again I will use the hydrostatic law between point 2 and 3. I will say that P3 equals to P2 plus rho GH, where now rho will be rho of water because water is filled between point 2 and 3. So rho of water G and H2. So P3 will be equals to 8829 plus density of water is 1000 into 9.81 into 2. So 1000 into 9.81 into 2 plus 8829. 28449 Pascal gauge again. This is mentioning this is always better whether it is gauge or absolute, right? So this is answer number 1 and answer number 2. You got answer number 1 and answer number 2. Clear? I hope you got how to solve this example. Now let us calculate another example. I have, so it is like calculate the pressure due to a column of 0.4 meter of water first, then oil with specific gravity 0.9 and mercury with specific gravity 13.6. Take density of water as 1000 kg per meter cube. So what they are asking is, they say that calculate the pressure corresponding to the column of 0.4 meter of 3 different liquids. So I have 3 liquid columns. One is water, oil and mercury, and all of them are filled with a height or column of 0.4 meters. In one column I have water, here I have oil, here I have mercury. Right. Now firstly let me talk about densities. Density of water is 1000 kg per meter cube. Density of mercury is specific gravity of mercury, Sg of mercury into density of water. Yes. So this will be 13.6 into 1000, which is 13,600 kg per meter cube. All right. And that for oil, if you see, it will be 0.9 into 1000, which is 900 kg per meter cube. I am putting it directly. So I got through densities. Now, what they are asking? They are asking to find out pressure due to this column. So pressure will be at the bottom point, right? All of them at pressure at the bottom point. So here pressure due to water column, this is pressure due to oil column and pressure due to mercury column. So here you know the pressure is atmospheric, PA, which is 0 Pascal gauge. Yes, all of them have atmospheric pressure PA at the top. So very simple. Use hydrostatic law in all of them. So firstly, if I take for water column, if I use the hydrostatic law, pressure at lower altitude point PW will be equals to pressure at higher altitude point PA plus rho GH. So PW equals to PA plus rho for water, G and H is 0.4 meters. Put the values. PW is equals to 0 Pascal and 1000 into 9.81 into 0.4. You will get 1000 into 9.81 into 0.4. 3924 Pascal gauge. Right? What about second oil column? Pressure for oil will be equal to pressure atmospheric plus rho of oil, G and H. H is again 0.4. This is 0. Oil density is 900, G is 9.81, H is 0.4. Find out the answer. So 900 into 9.81 into 0.4. 3531.6 Pascal. Pressure of oil. Pressure due to oil column, right? And third, pressure due to mercury column. So pressure due to mercury will be equals to what? PA plus rho of mercury, G and H, which is equals to 0 plus 13,600, 13600 into 9.81 into 0.4. 13600 into 9.81 into 0.4. You will get 53366.4 Pascal gauge. Now if you look very closely, the liquid column has the same height, but pressure at the bottom of the water column is 3924 Pascal. For the oil it is 3500 and for the mercury it is 53,366. What does it mean? Mercury has the highest pressure, water has intermediate and oil has the lowest. This basically is because of the density differences. So higher the density of the fluid, more will be the pressure corresponding to the same height of the column. Clear? Okay, let us calculate another example. The pressure intensity at a point in a fluid is given as 4.9 Newton per centimeter square. Find the corresponding height of the fluid when it is water and when it is oil of specific gravity 0.8. Now see here the question is reversed. They say that pressure given to you at any point is 4.9 Newton per centimeter square. Firstly, we will convert this into SI unit, that is Newton per meter square. How we will do that? 4.9 Newton. Now centimeter is how much? 10 to the power minus 2 meter, and then square of that. So this will be 4.9 Newton per 10 to the power minus 4 meter square. Minus 4 will come in numerator, will become plus 4. So 4.9 10 to the power plus 4 Newton per meter square. Alright. This is the pressure at any particular column. Now what they say? You need to find out the height. So simply we know that pressure for any point will be equals to pressure atmospheric plus rho GH. Normally we take atmospheric pressure to be 0. So pressure atmospheric plus rho of water, G and H of water. So pressure is given to you as this 4.9 10 raised to 4 equals to, this is 0, directly I'll put 0. Rho of water is 1000, G is 9.81, and I don't know what height of water column. I need to find the height. So 4.9 somewhere around 4.99 meters. This is the water column, answer number 1. Corresponding height for water is 4.99 meters, and that for oil will be what? P equals to P ATM plus rho of oil, G and H of oil. This is directly 0. So 4.9 pressure is same. You need to find out the corresponding column. So what is density of oil? Specific gravity given to you is 0.8. So density of oil will be Sg of oil into density of water. So this is 0.8 into 1000. So simply multiply specific gravity with 1000 to get the density of that particular fluid. 800, right? So this is 800 into 9.81 into H of oil. I don't know what is the answer, right? So I'll calculate this. The column will be much larger, around 6.24 meters. You see, the column for oil with the same pressure will be larger. Answer number 2. Clear? I hope you got how to solve this numerical. You understood this. Let us take another example. Determine the gauge and absolute pressure at a point which is 2 meters below the free surface of water. Take the atmospheric pressure as 10.1043 Newton per centimeter square. So I have been given a water, and I need to find the pressure at the depth of 2 meters from the free surface, right? So let us mark this point as 1, this point as 2. I know pressure at point 1 is what? Atmospheric. Now see, interesting point. I have been asked to find out the gauge pressure and absolute pressure at this particular point, right? So the equation says that P2 equals to P1 plus rho of water, G and H, because it is water. Now, if you substitute the value of P1 in gauge, then you will get this in gauge. If you put this value in absolute, you will get this in absolute. Now firstly, P1 should be known to you. So value of P1 in gauge, that is atmospheric pressure in gauge, will be 0 Pascal by default, right? So this is gauge, and value of P1 for absolute, it is given to you. Atmospheric pressure is 10.1043. This is the value of atmospheric pressure in absolute sense, right? So 10.1043 newtons per centimeter square. This is absolute value. So now you convert this to Newton per meter square. For that you will multiply by a factor called 10 to the power 4, if you remember, right? This will give you the value in Newton per meter square and absolute value. So this is P1. Now we will use this value and this value. So if now I want the value of P2 in gauge, firstly I will use P1 in gauge plus rho of water, G and H. So P2 will be equals to 0 plus rho of water is 1000 into 9.81 into 2. So P2 will be equals to this is 19620 Pascal, but this is a gauge pressure. Gauge value of pressure at point P2. Answer number 1. This you want, right? This is answer. Answer 1. Now, the same expression, you use it and you substitute the value of P1 in absolute sense. You will get P2 in absolute. So, what is value of P1 in absolute sense? It is this 10.1043 10 to the power 4 plus rho GH as it is 1000 into 9.81 into 2. So, this is around 120,663 Newton per meter square or rather Pascal. Both of them are correct, but this is an absolute value, absolute pressure, and this is answer number 2, this value. So I hope you understood how to solve the numericals on hydrostatic law. Thank you so much. For more such conceptual videos, you can log into our website www.clariconcepts.com. Thank you.